Good morning, dear students. Today we're having the 17th practical lesson, and we're starting a new topic for you. New topic, and this topic is related to series such infinite sums. So the general form of series of numeric series is the following. So this is a kind of series. So n sum where n starts from n, and some terms that depend on n. So this is the generic form of the numeric series. This series can converge or diverge. If series converge, we can calculate sum of series. So it means that so that its sum is not infinite. So let's start having practice with it. So we will have to calculate the partial sum. So in exercise 1, sum of the series prove its convergence using the definition of convergence of the series directly. Okay, so writing down the first series. So 1 over 1 multiplied by 3 plus 1 over 3 by 5 plus 1 over 5 by 7. And it continues to the infinity. Actually, what can we see here? So that this multiplier is less than, so the first multiplier is less than the second by 2. And in the next term, both multipliers are increasing by 2. So we see that that something, yeah, so we can see some закономерность. So some rule for which by which these terms increase. So we can write down the sum in a following way. So starting from n equals 1, yeah, actually sometimes n can start from 0, from 2, from another index. So the following sum. So 1 in the numerator, and here, so 2n minus 2 multiplied by 2n plus 2. So 2n minus 1 and 2n plus 1. So these numbers are odd, and we can see that they are really odd. And 2n minus 1 is less than 2n plus 1 by 2. So let's yeah, and actually the nth term of the series is the following. Okay, let's use un here. So it will be written in the following form. We will use undefined coefficients. So we will write this fraction as sum of fractions. So a over 2n minus 1 plus b over 2n plus 1. So copy and paste in denominator, common denominator. So having a multiplied by 2n plus 1 plus b multiplied by 2n minus 1. Uh, 2an plus a plus 2bn minus b. So regrouping this, regrouping all coefficients. So 2a plus 2b n plus a minus b. So we'll receive the system of linear algebraic equations. So 2a plus 2b equals 0, and a minus b equals 1. So it means that a equals minus b. So the solution of the system is the following. So we will receive here 2a equals 1. So it means that a equals 1 over 2 and b equals minus a. It equals minus 1 over 2. So we will rewrite un as so in the following form. Okay, let's write here. So 1 over 2 by 1 over 2n plus 1 and plus minus 1 over 2 by 1 over 2n minus 1. So this is the nth term of the series. And now let's rewrite all these terms like so. Okay, so let's write down the nth sum of the series. So how it is written? So k starting from 1 to n, so it's a partial sum of terms. And in our case, it will be like this. So it will be equal 1 over 2 sum of okay, let me write it in a more accurate form. And here n will be replaced to k. So having the following sum. So now writing it's in more detailed way. So substituting k equals equal to 1. So 1 over 3 by 1 over 3 plus 1 over 1, and then plus minus 1 over 1. Stop. Here will be minus, and here plus. So, and let me rewrite it. Yeah, let me change the order here. So 1 over 2k minus 1 minus 1 over 2k plus 1. So 1 over 1 minus 1 over 3. And here 1 over 3 minus 1 over 5. And then the third term 1 over 5 plus minus 1 over 7. Okay, let's write down one more term. So 1 over 7 minus 1 over 9. So as we can see that some terms are eliminated. So minus 1 over 3 plus 1 over 3 minus 1 over 5 plus 1 over 5 minus 1 over 7 plus 1 over 7. And it continues. Then let's continue to n. Okay, let me write this bracket in another. Okay, let me move to another line. So continuing it with other indices. Okay, let's uh, yeah, just a moment. Oh, plus is on my keyboard. Okay, sorry. So a little bit tired with the release this week. Okay, so now 1 over 2n minus 1 plus or minus 1 over 2n plus 1. Okay, let's also write one term that was before this term. So it will be written in the next form. So 1 over 2n minus 3 minus 1 over 2n minus 1. So actually what will remain here? If we eliminate everything, so we will have 1 over 2 multiplied by 1 minus multiplied by 1 minus this value. So it is the partial sum of the series. And how to find the partial sum of the series? We will have to calculate the limit of this partial sum when n approaches infinity. So, calculating the following limit. So, let's move 1 over 2 out of limit sign. And actually, we can see that if we substitute n, we will receive here will be 0, here will be 1, so the partial sum equals 1 over 2. And by the sum of the series equals 1 over 2, and by calculation this sum, we proved that the series is convergent. Any questions about this exercise?
Can you move a bit top?
Here?
Oh,
Or
no, yes, yeah. And I have the next question. Can you move again a bit top?
yeah?
Why is in the row where the last calculation by coefficients method, we have one minus 1 over 2, but not plus. I don't understand
Uh,
this. Yeah,
yeah, so b equals minus 1 over 2. So
but b with minus.
b equals, yeah, so we write down like sum of, so a divided by 2n minus 1, so a equals 1 over 2, so it is here. Yeah, so just order is different. So yeah, I believe it can be confusing. So
I understand.
a
Yeah.
equals 1 over 2, b equals minus 1 over 2, so that's why minus. More questions? Okay, if no questions, let's move next to the next exercise, 1b. We will calculate the following sum of the series. So arctangents of 1 over 2 plus arctangents of 1 over 8, and continuing. Plus arctangents of 1 over 2n square. And this sum, of course, is infinite. So, okay, we will not use the approach. We cannot use approach from the previous exercise, of course. So we will do the following stuff. So we will use method of mathematical induction. Do you know about it? Okay, if you have no experience in using this method, don't worry. We will have some exercise. So calculating firstly S1. So it will be equal arctangents of 1 over 2. So just the first term. Then S2 will be equal arctangents of 1 over 2 plus arctangents of 1 over 8. How to calculate? Yeah, we have, so there is a special formula. Let me write it down here. So arctangents of A plus arctangents of B will be equal arctangents of the following fraction. So okay, let me check here. Yeah, because I forgot it a little bit. So A plus B and 1 minus AB. So with this formula, so from trigonometry. So calculating these values. So 1 over 2 plus 1 over 8. And 1 minus 1 over 2 by 1 over 8. It will be equal okay, so in the numerator we have, so 1 over 2 is equal to 4 over 8, so 5 over 8. And here, so 1 minus 1 over 16 will be 15 over 16. So then arctangents over, so here will be, okay, 1, 1, 1 and 3, 1, 2. So it will be arctangents of 2 over 3. So found it. Now then S2 will, S3. It will be equal to S2 plus the third term, and the third term will be equal 1 over 32. So yeah, if I substitute n in power, oh, stop, n in power 3 will be equal to 8, so it will be equal 1 over 16. Stop. Why here 18? n in power of n in power of 2. So it will be 2 multiplied by 3 squared. So 1 over 18. So my bad. So calculating again with using the previous formula. So adding arctangents to over 3 plus arctangents over 1 over 18. So again, using the previous formula, so 1 over 18, and here 1 minus 2 over 3. multiplied by 1/18. So here will be 12/18 plus 1/18, so 13/18. Then, okay, so here will be 1/27 here. And if I subtract 1, so 1 minus 1/27, it will be 26/27. Okay, and I will receive. So here will be 2, and here will stop. Here will be 2, and here will be 3. I'll stop.
Too short.
Yeah, but I guess that something is wrong here. Yeah. Okay. Just okay. Let's let's simplify it one by one. So here will be 1, here will be 2. Then here, so here we can divide by 3. So here will be 6. We can divide by 9. So here will be 2. Here will be 3. So we will receive arctangents over 3/4. So what do we have now? Arctangents of 1/2. So S1 equals arctangents 1/2, S2 equals arctangents over 2/3, and S3 equals arctangents over 3/4. Do you see maybe some rule, or we need to calculate a little bit more? So once more to sum S4, or is it enough for you to see the rule?
Can we calculate one more?
Okay, let's do it. So S4 will be equal, so arctangents over 3/4 plus arctangents over 1 over, so 2, so 1/2n square, so 4 square equals 16, so 1/32. So calculating it. So 3/4 plus 1/32. 1 minus 3/4 by 1/32. So calculating it. 3/4, okay, multiplying by 8, it will be, so 24/32, so 25/32. And here 3/128. So 128 here, and 125. So now canceling what we can cancel. So dividing it by, so here will be 1, here 5. Then I can divide this value by 32, and this by 32, it will be 4. So I receive arctangents over 4/5. So the following rule that we have. So S1 equals arctangents of 1/2. Then S2 equals 2 over 3. S3 equals 3 over 4. S4 equals 4 over 5. So do you see the rule?
Yeah.
So, okay, what about the nth member, the nth term of the series? So, okay, let us suppose that it will be equal n over n plus tangents of n over n plus 1. But we also need to prove it. So we need to prove that s n plus 1 will be equal Sn plus n plus first term. So plus, okay, here will be n plus 1 and here n plus 2. Here n plus 2. So again, using the previous the formula that we used previously, so n by n plus 1 here plus n plus 1 over n plus 2 and 1 minus n by n over n plus 1 and here n plus 2. So continuing calculating, so n by n plus 2 plus n plus 1 square. Then here will be n plus 1 by n plus 2. And here will be the same denominator. And I will receive here 1 minus n by n plus 1. So we will simplify this fraction a little bit. So this will be numerator, and this will be denominator. So now expanding brackets and regrouping members. So n by okay, n square plus 2n plus n square plus 2n plus 1. And here 1 minus n square minus n. Okay. What can be reduced here? I don't see it for now. Okay, let me check my notes. Yeah, so it was regrouped here in the following way. So moved n plus 1 out of brackets. So actually, as we can see here in these notes, that yeah, it really will be equal. So n plus 1 by n plus, oh, yeah, it was incorrect here. So it must have been n. So 2 by n plus 1 square. So what was the mistake? Okay, but now let's just believe my notes that it. So after we do a lot of transformations, we will receive that Sn will be equal n plus 1 over n plus 2. So we proved that Sn equals arctangents of n over n plus 1. So this is the method of mathematical induction, how it works. So now calculating the sum of the series. So again, it will be the limit of Sn when n approaches to infinity, So calculating this limit of such arctangents, and it will be arctangents of 1, and it will be equal P over 4. So this is the sum of the series. Any questions about this exercise?
Probably no for now.
Okay, so now let's continue and having one more such exercise, and after that we will probably have a break. So 1C. So the following series. So n starting from 1 to infinity. 3 in power of n plus 2 in power of n, and divided by 6 in power of n. So received the following series. Actually, we can 3 in power of n. We can do the following stuff. We will divide it by 6 in power of n, and we will receive the following sum. So 1 over 2 in power of n plus 1 over 3 in power of n. And we can write it down like sum of two series. So here will be 1 over 2 n, and here will be 1 over 3 in power of n. Okay, so we will so we split this series to two separate, and let's calculate for each of them separately. So what about this series? So 1 over 2 plus 1 over 1 over 4 plus 1 over 8 plus 1 over 16 and so on. So what do you actually see? So actually this is a geometrical progression with the first term. Yes, Stanislav, question?
Why do we have 1 divided by 6 after 1 divided by 8? Maybe by 16?
I just missed one, yeah, misclick, thank you. So we have the geometrical progression with the first term a equals 2, and the denominator of this progression as well 1, so 1 over 2. And how to calculate the sum of the infinite geometrical progression? So so this sum will be calculated in the following form. So this geometric progression is infinitely decreasing. So the sum of the infinitely decreasing geometric progression. So how to calculate it? So let me write down it like this. So Sn, and here will be 1. So for the first term, well, it will be written like this: A1 over 1 minus Q. Okay, let me write down like Q1 here. So the following formula. Okay, let me check if I didn't forget it. Yeah, so yeah, A over A1 minus Q. So 1 over 2, and here will be 1 minus 1 over 2. And it will be actually equal 1. So, and it is the sum over of the first series. Okay, let me write down it like this. So what about this series? So we have 1 over 3 plus 1 over 9 plus 1 over 27 plus 1 over 81 and so on. So again, we have the infinite geometric progression. So it is geometrical series, by the way. So it is infinitely decreasing geometric progression. The first term is 1 over 3, and the denominator is 1 over 3 as well. So how to calculate this sum? So we will do the analogical stuff. So this using the same formula. So A2 divided by 1 over by 1 minus Q2. So 1 over 3, and here will be 1 minus 1 over 3. So 1 over 3 by 2 over 3. So it equals it will be equal 1 over 2. So the sum of the series will be the initial series of this series will be equal to sum of this sums separately. So S1 plus S2. So it will be equal 1 plus 1 over 2, so 3 over 2. So, and that's it. Let me check with my notes. Yeah. And by the way, so let me remind you that the geometric series converges only if the denominator q is less than 1. So any questions about this exercise?
No questions.
Okay, no questions. Now let's have a break for 5 minutes, and after that we will examine a series by convergence.
Can I ask a question?
Yeah.
I don't see check-in for today's practice.
Okay, let me see. That's weird. It must be okay. Maybe something wrong in time or group. Just a moment. Yeah, I made a mistake. So I created attendance for another group. So let me okay, stop. Let me check. Maybe there is also for the first group practice as well, because I don't hold practices there. Just a moment. So of course I will fix it. Let me check timetable. Yeah. So there is attendance also for the first group. Okay, I will create it for you. Just a moment. Yeah, I just made the wrong date. I created it, but for Monday. Now you will be able to check in. So try, and I guess it will be work for you now.
It says that I got automatically checked in,
Okay.
but
Yeah.
I was absent.
Okay, yeah. So let me recreate. Just a minute. So don't worry about it. So yeah, and that's because the deal automatically so selects the date for today. So now you must have the ability. So refresh the page and try if it works for you.
Yes, it does. Thank you.
Okay, so now let's have a break for 5 minutes and then we will continue. Solving interesting tasks. Okay, let's continue. So yeah, it was a little bit longer than I supposed. Okay. So now we will use different tests to check to investigate the convergence of the following numerical series. The first, or 2A, we have the following series. So now from n to 1, infinity, by infinity. And the series is the following: 1 over square root of n square plus 2n. So let's check the nth term. So let's check the nth term. So un equals this expression, and it is so when n approaches infinity, it is actually equivalent to the following. So 1 over n. So we will compare this initial series with uh, with the harmonic series that diverges. So the following series, and we can see that un. So actually 1 over so this value is less than, oh no, it's great, yeah, it's greater than stop, is less than this value. Yeah, and yeah, okay, well, they're equivalent, so it's not, doesn't really make sense to compare in such way. So actually, yeah, so as this series are equivalent and harmonic series diverges, it means that initial series is divergent. So the final answer will be the following. So divergent. So any questions about this exercise?
No questions.
No questions. Okay.
No.
Now having the doing analogical exercise 2B. N plus 1 over 3n over 3n square over 3n cube minus 2n. So un equals the following series, the following, so nth member equals the following expression, and when n approaches infinity, this series is equivalent to 3 over n square. Let's compare with the generalized harmonic series. So with the generalized harmonic series, which has the following form: 1 over n square, and generalized harmonic series converges when this degree p so greater than 1. So in our case, it's greater than 1. So this series is convergent, and this series is actually less than this series. So this series is less than this series. this series is convergent, so the initial series is convergent as well. So any questions? Yeah, so this series convergent. So the initial convergent as well. Okay, let me write like this. So any questions? I guess that no questions. Now let's continue. So to see, we have the following series 5n square plus 1 over 7n square minus 4. So what can we check here? So actually the un, so nth term equals this value. And what do we remember? So that necessary condition of convergence. So the necessary condition of convergence that it must, so the limit of the nth term must be equal to 0. Let's calculate limit of nth term here. So it will be the following. It will be equal to 5 over 7. And it is not equal to 0. So we just used the divergence test. So according to this, the initial series is divergent. So for A and B, we used comparison test, and for C, just divergence test. So any questions about this exercise?
No questions.
Okay, no questions. So with solving all these exercises, you will know how to define which test to use. So now the next example. So we have the following expression. So 1 over n, and in brackets square root of n plus 1 minus square root of n minus 1. So first of all, let's rewrite this expression in the following form. So we will multiply and divide by the conjugate. So doing this stuff. So here will be plus, and here will be plus as well. So now let's expand brackets. So what do I have here? N minus n plus 1 minus n minus 1. And here the denominator remains the same. So what I will receive? So I will receive n and this expression. Then when n approaches infinity, this expression, yeah, by the way, it is the nth term. So this expression will be equivalent to 2 over 2n and the square root of n. So considering this members, and it will be equal to 1 over n square root of n. So let's have a look at this series. So n equals so n from 1 to infinity, and this series. Actually, it's a so generalized harmonic series with the power over 3 over 2 that is greater than 1. This series is convergent. And it means that the initial series is convergent as well. Any questions?
No.
Okay, no questions. So go into 2e. So we have the following series. So n from 1 to infinity. And yeah, so it can scare you. So trigonometry. So then, so sine of p in power divided by 2 in power of n. So actually, what can we say about this series? So about the nth term. So so when n approaches approaches infinity, so the argument of sine approaches 0. So this term approaches 0 as well. Okay, let me remember what I did here. Yeah, so as n approaches infinity, so when n approaches infinity, this nth term is equivalent to the argument. So sine is equivalent to the argument of the sine. And what can we say about this series? So actually, we will receive the following series. Just okay. Okay, hotkeys. So from n to from 1 to infinity. So the following. Let me also move p out of brackets. And what we will actually receive, it is a geometric a series that is that has so geometric series, and here so a1 equals 1 over 2, and so the denominator q equals 1 over 2. So as q is less than 1, so this series is convergent. So the initial series is convergent as well. So is it clear? Any questions?
No, no.
Okay. Now continuing. So in the next exercise. So here we having the following a series. So 3n plus 1 factorial over 8 in power of n square. So what we will use here? We will use the D'Alembert test. Let me remind you how to use it. So we will calculate the following limit. So when n approaches x, so we need to calculate okay, let me check which of them. Sorry. If I'm not mistaken, we need to calculate so un plus 1 over un. And if this limit equals, so okay, let's calculate it as c. So then if c if c is greater than 1, so divergent. If C is less than 1, the series is convergent. If C equals 1, it is unknown. If so, we cannot say if it is convergent or not. So we will have to use other tests to provide more investigation. So here we will use Downberg test for such a series. So let's write down UN. UN will be equal the following. So the following expression. And what about UN plus 1? So it will be equal. Okay, so UN plus 1. Substitute an n plus 1 here. So it will be 3n plus 4 factorial, 8 in power of n plus 1, and n plus 1 square. Then calculating the limit. So the limit will be the following. So writing down this expression now I will move to nowhere this fraction. So having this expression. So what can we simplify now? So actually n plus 1 square and n square are equivalent when n approaches 0. What about 8 in power of n? I will cancel 8 in power of n. So here will remain 8, and I will just move it. I will move it here. So having the following limit. And now let's also rewrite this limit. So we will transform this factorial. So actually what I will have here, so 3 plus n factorial will be cancelled, and actually there will be no fractions. So what I will have, so 3n plus 2 by 3n plus 3 by 3n plus 4. And it will be equal to infinity. So it means that initial series is divergent, according to Downberg test. Any questions about this exercise?
Why this member u plus n plus 1? In the denominator we have 3n plus 4, but not 3n plus 2.
Okay, so I substitute. Okay, let me write it in details. So 3, I substitute here n plus 1 instead of
I understand.
Yeah, so and then expand brackets and receive the following expression. More questions?
No questions.
Okay, if no questions, let's move to the next exercise. We even solved F, so now moving to G. So the following series. So 2 by 5 by so and so on by 3n minus 1. And here 1 multiplied by 5 multiplied by, okay, and so on. And finally multiplied by 4n minus 3. So the following series. So the nth term is the following. And what about n plus 1? So multiplied by 3 n plus 1 minus 1, and here 4n plus 1 minus 3. So let's expand it. So I will rewrite. So 3n plus 2, and here will be 4n plus 3. Yeah, and forgot to multiply by this expression. So the following series. So now let's use the D'Alembert test. Okay, let me move C here for my convenience. So using this formula, forgot about this multiplier. So multiplying this expression and by this expression, but first of all, turning over the fraction. So what can and of course let we not lose a limit sign. Okay, I'll write it down like this. So what can we cancel here? We can cancel this part and this part. So cancelled. And we can cancel also this numerator and this multiplier. So canceling. Actually, I will just erase it. And what I will receive? So the following limit. And it will be equal 3 over 4. It is less than 1. So, according to D'Alembert test, the initial series is convergent. Any questions about this exercise?
No questions.
Okay, no questions. So, moving next. Okay, let me leave this formula as well. So, we'll save our time. So, 2h. N by tangents over p over 2 in power of n plus 1. So the nth term actually we will just copy and paste from the series expression. And here I will write down, so n plus 1. And here will be tangents of p over 2 of tangents p over 2 in power of n plus 2. So now calculating the limit. So this expression, taking this expression and this expression. So what can we cancel? We can cancel n and n plus 1 because they are equivalent. So received the following limit. Then, as arguments of tangents are, they are approaching, so they approach 0. So the argument of tangents is equivalent to tangents. So doing like this. So now canceling p. And what I will actually have, okay, I will write like this. So here will be 2 in power of n plus 1, and here will be 2 in power of n plus 2. And actually it will be 1 over 2. that is less than 1. So it means that initial series is convergent according to D'Alembert test. Any questions about this exercise? Let me also check.
No.
No?
No.
Okay, let me check the solution. Yeah, so actually it's an analogical. Then the next series. Not now. Okay, the next series, so it will be the following. Okay, let me check it. Yeah, okay, and now we will not use D'Alembert test. We will use another test. So I will first of all write down the expression of the series. So the nth term is the following. So n over 2n plus 1 and in power over n. And un actually equals this expression as well. We will use radical Cauchy test. Let me remind you what does it, so how to use it. So we will have to calculate the following limit. So when n approaches infinity, so the following limit, so limit of root of power of n over the nth term. So the following test. And again, actually the conditions are the same. So if this limit is greater than 1, this series is divergent. When c is less than 1, the series is convergent. When c equals 1, we cannot say. So let's calculate this limit with using a radical Cauchy test. Why? Because we have n, so here we have the power of n, so it will be really convenient for us. So substituting this expression, so what I will have here, I will have the following limit. And we can easily see that it is equal 1 over 2. It is less than 1, so the series is convergent according to radical Cauchy test. Any questions about this exercise?
No.
Okay, no questions. So writing down the next series. 1 over 3 in power of n and multiplied by 1 plus 1 over n and n in so in power of n square. So here again we will use radical Cauchy test. So opening this root of power of n, and what I will receive 1 over 3 and 1 plus 1 over n in power of n. So now what I'm doing, so moving 1 over 3 out of brackets, and according to the second perfect limit, this limit will be equal to e. So I will receive e over 3. And e equals something about 2.72 and so on. So this expression is less than 1. So according to radical Cauchy test, the initial series is convergent. Okay, convergent. So any questions about this exercise?
No.
Okay, no questions. And now we will use one more test. I forgot to about numeration. So here we so skipped I and J, but really solved them. So the following series. So n from 1 to infinity, and the following series. 1 over n plus 1 logarithm square of n plus 1. Here I will use integral Cauchy test. How to use it? As we can see, this nth term is actually so looks like we can integrate it. So it looks like so it looks like convenient for integration. So how to use? We will have to calculate the following integral. Integral from the starting index of n. So here will be 1. So from 1 to plus infinity. And so we will integrate the following function. So we will calculate the following integral. And according to integral Cauchy test, the initial series will be convergent when this integral convergent as well. And if integral diverges, series diverges as well. So here we will use the differential entry technique. So we are having the differential of logarithm of n plus 1 or x plus 1. And I will receive minus 1 over this logarithm. With substitutions from 1 to plus infinity. So if I substitute plus infinity, I receive 0 here. If I substitute 1, I receive 1 over logarithm of 2. And don't forget about minus here. So it will be equal 1 over logarithm of 2. So integral is convergent. And series converges as well, according to integral Cauchy test. So, any questions about this exercise?
No.
Okay, no questions. So now let's solve the last exercise for today. Yeah, so it's really the okay, let's skip this. I forgot about the third exercise. So okay, so you will solve it in your own, and now I need to show you one more exercise. So 3a, we have the following series. Before we investigated series with only positive coefficients, and here we have a series with different coefficients with coefficients that change the sign. So let's check this series. So un equals this value, and actually, yeah. So let's investigate the series of some module of this series, and we can see that this term is less than 1 over n in power of 3. And the term this term is a harmonic this term is a generalized harmonic this series is generalized harmonic series that converges because module equals because this power equals 3. As a module of this series converges, it means that the series converges absolutely. It converges and converges absolutely. If the series was convergent, if this series, so it could be convergent absolutely or conditionally, but it is converges absolutely because the series of modules converges. Any questions about this exercise?
No questions.
Sorry? Okay, no questions. So let's skip B and move to the 3C, more interesting case. So we have the alternating series. So what does alternating series mean? That the sign of it is alternate. So according to n. So 1 over so minus 1 in power of n by 1 so multiplied by 1 over n over square root of n. We will use Leibniz test. According to Leibniz test, the nth term, so the modules of nth terms must be the sequence of nth sequence of modules of terms must be decreasing. And so the nth term is the following, so module of the nth term. And what about un plus 1? It will be equal 1 over n plus 1. What can we see here? That un is greater than n plus 1. So this series converges. But we need to investigate if it converges absolutely or conditionally. So we need to investigate the following series. Actually, we have the generalized harmonic series with the power of 1 over 2, and it is less than 1. So less or equal than 1. So this series is divergent. It means that the initial series converges conditionally. Actually, there are two ways how to investigate such terms. You can start investigating you can start investigating series that consists series of modules, and if the series of modules is if the series of modules is convergent, so you can write down that the series is convergent absolutely, and you will not have to use Leibniz test. But if you investigate the module, start investigating module, and you see that it is divergent, you need to check if the sequence of members is decreasing. So there are two approaches. Any questions about this exercise?
No.
No.
Okay. Okay. About the whole lesson, about previous lessons, maybe.
No questions.
Okay, if no questions, let's finish for today. Thank you for your attention. Stay safe. Goodbye.
Thank you. Goodbye.
Thank you. Goodbye.
Thanks for the lesson. Goodbye.
Bye.